Hello everyone. We are now on our week 10 and today we are going to talk about partial differential equations and then the advection equation, the diffusion equation, and some numerical methods for the diffusion equation. So first, what is a partial differential equation? So until now we just study some ordinary differential equation in which we have ordinary derivatives, which means that we have some total derivative, and therefore we have only one variable. So we see that our function u is a function u of x, or u equal u of t. But now on partial differential equations, we have more than one variable, and then u would be some function of time and space. Okay, so this this kind of equations have some classification. Okay, so this notation here, uxx, is simply so uxx is del u del. So it's the second derivative of u into respect to x, and then so here we are considering that our u is a function of y and x. Okay, so and then uxy is del u del x del y. So first we derivate our u in respect to x, and then we derivate it into respect of y, and then we have del u yy, it's just the second derivative into respect of y, del u x, del u y, and then we have some u here and some g. So now we are considering that we have a, b, c until g constants, and then the classification of this partial differential equation, which will each kind of PDE has some different behavior, and therefore a different kind of numerical method must be used to solve each kind of equation. So this classification depends on the sign of the discriminant, which is given by b squared minus ac, so just depends on these terms here. So if this delta is negative, we say that our PDE is elliptic, and if this delta equals 0, is parabolic, and if it's bigger than 0, then it's hyperbolic. So let's see some example for each kind of PDE. So one example of elliptic PDE is the Poisson problem. So this operator here is the Laplacian. Okay, so elliptic equations models typically steady state or equilibrium phenomena. There is no temporal dependence. So for example, we could think about the steady state of the heat equation. So this term here is the Laplacian, and I don't know if you remember, but so if u equal u of x and y. The Laplacian of u will be del u del x square plus del u del y square. So if we apply the Laplacian operator at u, the scalar function u, is simply this relation here, okay? So so we seek for a function u of x, or it could be u of x and y if it's 2D, okay? So here is a 2D problem. So u of x is if it's 1D. So we seek for a function u of x that satisfies the equation with some boundary conditions. As we have seen before, it could be Dirichlet or Neumann, okay? As parabolic, as example, we have the heat or the diffusion equation. In this case, we are not interested anymore on the steady state only, but we are also interested on the change of u along time. So we could have our u, so if we are in the 2D, we have that u equal u of t, x, and y, for example, okay? So this equation is known as heat or diffusion equation. So if you look at this equation, F would be a source or sink. So think about that you have a metallic string and that we have some source of heat here, which is F, and then how this heat distribute along this bar, 1D bar. It would depend on the Laplacian of u, okay? So the effect of the diffusion usually is to make things homogeneous, okay? So if you start with some concentration like this, of some heat distribution like this, the tendency is to reach some homogeneity, okay? So it will be just doing like this. So like this, and then so the peak should be here, okay? And so depending on your boundary conditions, if you have Neumann boundary conditions, mean that your bar is isolated on its edges and no heat can come out or come in the system, and therefore the total energy of this system is constant. Or if you think about diffusion of particles, and you are in an isolated system, you don't let the particles go in or out, the total mass of the particles in this system would be constant as well. So imagine that you have a plate with water, and then you put some drop of ink in the middle of this plate. Then the ink will spread away, and if you wait long enough, at some point it will be just some homogeneous concentration here of so the ink will be equally distributed all over the space. Okay, so this equation, it requires initial conditions at the initial time t equals 0 for every spatial point in the domain, and the boundary conditions at each time t bigger than 0. We are still define it mathematically in a better way. It's just for you to have an idea. And then we have hyperbolic kind of equations, and then we can just describe one example of it is the wave equation. So we have del u del t equal a plus del u del x. So a in this case is velocity. So the behavior of this function. So if we have as initial condition some function like this function would move with velocity a in this domain. Okay, so the initial function wouldn't change its shape, so the diffusion would make something like this. But in this case, where you have only a velocity, you have your wave moving in a direction, a constant direction, and it doesn't change. So if a is positive, it moves to the right, and if a is negative, it would move to the left. So this equation models wave motion, and the solution is periodic. Okay, that is, you can determine it. So it will depend only on the initial condition at t equals 0, and then it will be just shifting, okay, in to the right or to the left direction depending on the sign of a. So now we are going to introduce conservation equations, and the objective here is to get into how we get the advection equation, or this wave equation, just by thinking about physical principles. Okay, so in physics, in an isolated system, there are many properties which are constant over time. For example, the total energy, the total momentum, or the total mass. So we consider that we have a tube. It's a 1D tube, and a flux of particles is coming from the left to the right, and we have some cross section areas A, okay, and then we are going to define C of xt as the particles concentration, which has the unity of number per volume, okay, number of particles per volume. J is the particles flow, so it is the flow unity is number times area divided by time, so it's how much number of particles cross areas section per time, so it's a rate. And we define also a function sigma x of t as some source or sink density rate, number per volume times time. So the total particles on the interval x plus j changes due to the flow of particles going in and out the interval x plus delta x, and the introduction or degradation of particles on the interval through chemical reaction, for example. So it's related to that sink or source constant. Okay, so we have here our tube, and we are interested on the change in this interval x and x plus delta x, and we have some flux coming in here that we call it J, and also we can consider some sink, so adding, or could be positive or negative. So if it's positive, we are adding something, and if it's negative, we are losing something. Okay, so we can just say that the rate of change of the particle population in this interval per unit time will be the rate of entry into this interval per unit time minus the rate of departure. So it's what comes in minus what goes out, plus or minus the source or sink variation on time. Okay, so we want to calculate this variation. So before that, we are trying to look for the dimensions of the quantities and try to write how this rate of these particles change over time. So A is the cross-sectional area of the tube, which has the dimension of area, which is meter square, centimeter square, something like this. So the variation of the volume length element. So we are like kind of wanting to see a small variation at this interval x and delta x plus delta x. So so if we are on the interval x plus delta x, the volume change in this interval will be A times delta x, because this is the cross-sectional area and the size of this interval is delta x. Okay, so let's look to the units. We know that C, the concentration, is number per volume. J, the flux. So here is concentration. Here is the flux. And here is the sink or source. Okay. So J, the unity of J is number times area divided by time. Sorry for the mistake here. And the sink or source has unity of number divided by volume times time. So we can just write that the variation of the concentration along time which is just that we wrote before only with words, so that this change over time. So just remember, let's see if the unit is matched. So C has the unity of number per volume, and A is area, okay? So A delta X is volume, okay? So if we multiply this by this, we will have number per time. So we want to know the number of particles, the change on the number of particles per time. And here we have J times area. So remember that J has the unity of number times area divided per time. Okay, so this area here cancel with this, and then we have something with number per time. So because of this equality, everything that is on the left hand side should have the same unity of the quantities that are on the right hand side. So these are the flux, the influx. Okay, so what's come in minus what's goes out. And plus or minus the sink or source. Okay, so and our sigma function has the unity of number divided by volume times time. Okay, and then if we multiply it by volume, this will cancel with this, and again we have number per time. So the unities matches, so it makes sense to think in this way. So if A is a constant area, so the cross-section area is constant, we can put it out here, okay? And then we have A multiplying everything, and we can just cancel A. And then del C, del T will be equal. So now we are dividing everything by delta X. And here already has this term, so this term here gets doesn't get divided by it. So we get this relation here for the variation of the concentration over time, and if we make delta X goes to 0, we just see that this quantity here, if we take the limit of delta X going to 0 of this, okay, then we will simply have the derivative of J, okay? So it's minus because if you remember, the derivative del J del X will be the limit of some H going to 0 of J X plus J H minus J of X divided by H, okay? So that's why here we have this minus, okay, because the sign here is just changed, and here is the net motion plus or minus the source or sink. So we got some differential equation for the change on time of the concentration of particles. Now a natural question would be, and how J looks like. okay? Because we have here some equation on C, and we want to define J as function of C, okay? So if the fluid is moving with velocity v, the flux of the particles is c times v. Let's just see if it matches the unity. So c has the unity of number divided by volume, and v, the velocity, is space divided by time. And therefore, if we make c times v, the unities of it would be number divided by volume times space divided by time. So remember that volume is space square, okay? So volume a square nowhere to the third, like space to the third, and therefore it would be number divided by area times time. Okay, so this flux unity was correct, where before I said that it was not correct, so sorry for that. So it was not right here, so here it was not correct. So it's number divided by area times time, okay? So so our J here has actually a unity of flux. So substituting this, so now we have a function. We can define the flux as depending on the concentration C, and then we can substitute on the equation that we got before, which was del C, del T equal minus del J del X plus or minus sigma. So here I'm consider the sigma equals 0, and then if we substitute this relation for the J, and therefore we get the advection equation, okay, which is basically the same of the wave equation that we have seen before. So if we are in 1D, we have that C, the concentration, is a function of T and X, and therefore the advection equation will be del C del T equal, so here is the gradient operator. So if we are in 1D, it will be just del C del X. So it will be del C del X. There is a minus here. So V is constant. If V is constant, it goes out of this gradient operator, and then we get del C del T plus V del C del X equals 0. So that's the advection or wave equation that we have seen before. Okay. Now we are going to start to talk about diffusion, okay?